Hi guys, welcome to a new video on optimization under math studies. This video shall continue with challenging questions, and similar to the previous video, it shall feature questions that have cylindrical objects. I shall attempt to solve the two questions on the screen in front of you, and I shall begin question 1 shortly. The first question that we shall solve came in paper 2, November 2016, question 6. Kindly take a minute and attempt to solve, and the answer shall follow through shortly. So we are told that a water container is made in the shape of a cylinder with internal height h and internal base radius r. The water container has no top. The inner surfaces of the container are to be coated with a water-resistant material. Write down a formula for A, which is the surface area to be coated. Now, since the water container has no top, we shall only calculate the curved surface area plus the area of the base, and this shall suffice to give us an expression for a formula for A. So A equals area of the bottom plus area curved, and we know that the bottom area is pi r squared because this is the area of a circle, and the curved area is equal to the perimeter multiplied by the height, so 2 pi r times h. Next, we are told that the volume of water is 0.5 meters cubed, and we are required to express this in centimeters cubed. So, to convert from meters to centimeters, we multiply by 100. Hence, to convert from meters cubed to centimeters cubed, we shall multiply by 100 cubed, or 100 times 100 times 100, which is 1 million. So the answer shall be 0.5 times 1 million, and this shall equal 500,000 centimeters cubed. Next, we are told to write down in terms of R and H an equation for the volume of the container. And the volume of the cylinder is well known. It is equal to pi r squared h. So this is the answer to C. In D, we are required to show that the area is equal to pi r squared plus 1 million over r. So let's take a look. So what we want to do is to find an expression for A in terms of r only. And there is our original expression. It has both r and h. So what we're going to do is we're going to eliminate the h by using this expression for volume in order to isolate the h and find an equivalent expression in terms of r. So since v equals pi r squared h, we can rewrite this as h equals v over pi r squared. I have simply divided both sides of this equation by pi r squared, obtaining this red expression right there, which I shall then substitute into this h right there, getting me an expression for A equal to pi r squared plus 2 pi r times v over pi r squared. This is exactly the same as this expression right there. The only difference is that instead of the h, I now have v over pi r squared. Now, we can simplify this blue expression a little bit. We can cancel the pi, this pi right there with the pi in the denominator, and we can cancel the r right there with one of the r's in the denominator, and we are left with 2 times v over r, which is this green expression right there. So the area is equal to pi r squared plus 2 times v over r. And since we already know that v is equal to 500,000, hence the area is equal to pi r squared plus 2 times 500,000 over r. 2 times 500,000 gives us 1 million, which helps us obtain this expression in gold, equivalent to the one provided in the question. Next, I'm told that the water container is designed so that the area to be coated is minimized. Find dA by dr, so I simply need to differentiate this expression for A right there. So I begin by taking this r in the expression for A and placing it in the numerator as r to the power of -1. This shall help me differentiate, and my derivative expression is A dash equals 2 pi r minus 1 million r to the power of -2. Next, we are told, using your answer to part E, find the value of r which minimizes A. So the value of r which minimizes A is the value of r that sets A dash to 0. So I need to find an expression for A dash, which I already have found in E, and then I need to equate this expression to 0. So there is my expression for A dash. I shall simply equate this to 0, and you can use your equation solver to find the value of r. I have simply modified the expression a little bit before using the equation solver. I've multiplied both terms by r squared in order to get rid of the negative exponent, obtaining this expression in gold right there. And I shall then use the GDC, as you shall see, in order to solve this equation. I am now attempting to solve this equation in gold right there. I shall type it onto the calculator. First, I shall press on math. I shall press up and then choose solver, and I shall type down my equation. There is my equation, and then I shall click on enter. I shall provide a guess, so let's just assume 5, and I shall press on alpha, solve, and the calculator tells me that x equals 54.1926. Hence, this is my solution for r. Next, I want to use the answer. Excuse me, we've already covered that. I want to find the value of the minimum area. So in order to find the value of the minimum area, I shall plug the value of r that I found in F into the expression that we found in D right there. So there is our value of r, and there is our expression of A right there, or right there, you can choose whichever one you want, and I shall simply plug the value of r into this equation, obtaining this purple equation right there, which you can easily evaluate on your GDC, and the minimum area is 27,678 or 27,700. Finally, I'm told that 1 can of water-resistant material coats a surface area of 2000. I want to find the least number of cans that will coat the area in part G. So I shall simply divide my area by 2000 in order to get the number of cans that I need to coat the cylinder. So if 1 can coats 2000, I just want to see or to figure out how many cans I need. So I'll just divide the area by 2000. The area was 27,678, so I just divide that by 2000, obtaining 13.8. Of course, there is no such thing as 13.8 cans, so I need at least 14 cans in order to coat my cylinder. So this wraps up this question. Kindly take a minute to write the answer down, and I shall begin the next question shortly. So the second question that we shall solve came in paper 2, May 2018, time zone 1, question 6. Kindly take a minute and attempt to solve, and the answer shall follow through shortly. So we are told that the manufacturer makes trash cans in the form of a cylinder with a hemispherical top. The trash can has a height of 70 centimeters. The base radius of both the cylinder and the hemispherical top is 20 centimeters. So make sure that you understand that this is the radius of the base of the cylinder, and it is the same as the radius of the hemispherical top because they share a common base. So the top base of the cylinder is the same as the base of the hemisphere. It's the same base. So of course it has the same radius. So in A, we are required to write down the height of the cylinder. This comes from the knowledge that a sphere has radii. So if this is the radius of the sphere or the hemisphere and this is equal to 20, this red line right there, then we should know that this line right there, vertically right there, is also equal to 20 because this is also the radius of the hemisphere. Hemisphere means half of a sphere. So a sphere has radii, an infinite number of radii in all directions. So all of these radii have the same length, which is 20. All of these red lines that I'm drawing have a length of 20. So what we are interested in is the vertical radius, which extends from the top of the cylinder to the top of the hemisphere. This is equal to 20. And since this entire line is equal to 70, therefore the height of the cylinder shall equal 70 minus 20, which is 50. Hence the answer to A is 50. In B, we are required to find the total volume of the trash can, and this shall equal the sum of volumes of the cylinder and the hemisphere. So the volume of the cylinder is given by pi r squared h. The volume of a sphere is 4 over 3 pi r cubed. Hence the volume of the hemisphere shall be half times 4 over 3 pi r cubed. So let's take a look. So in order to calculate the total volume of the trash can, I shall add the volume of the cylinder and the volume of the hemisphere given by these equations which we have just mentioned. Knowing that the radius of the cylinder and the radius of the hemisphere are both 20 and they are both going to be always equal because they share the same base. So let's plug in the values into the red equation. R cylinder equals 20, H cylinder equals 50 from A, and R hemisphere equals 20. Hence the volume shall be 79,600. All I've done is I've plugged the values we've agreed upon into the red equation right there. So this concludes the first part of the question. Let's move on to the rest of it. This is the rest of the question. You might want to pause the video and attempt to solve before I continue with the answer. So we are told a designer is asked to produce a new trash can. The new trash can will also be in the form of a cylinder with a hemispherical top. This trash can will have a height of h and a base radius of r. There is a design constraint such that h plus 2r equals 110 centimeters. The designer has to maximize the volume of the trash can. Find the height of the cylinder h of the new trash can in terms of r. This is the same concept as what we've done before. We have a total height h capital, and we know that this part right there is equal to r small. Hence, the height of the cylinder, which is represented by h small, shall equal h capital minus r, which is this part right there. this part that I'm drawing right now, h small, shall equal h capital minus r. If you are unsure of how we've derived this, this is the value of h capital, this is the value of r, hence h small, which is the height of the cylinder, shall equal the difference between both. In D, I'm required to show that the volume of the new trash can is given by this expression. So in order to find the volume in terms of R, we need to eliminate H. So first we consider the given constraint, which is that H capital plus 2R equals 110. Hence H capital equals 110 minus 2R. And since we know that the height of the cylinder is H capital minus R, which we have derived in C, we can say that the height of the cylinder, which is H capital minus R, is equivalent to 110 minus 2R minus R. So how did I reach this expression? Simply by putting 110 minus 2R instead of H capital, hence arriving at this expression. Hence, the height of the cylinder shall be 110 minus 3R, which is the sum of these two terms. So I want to find the volume of the trash can, which is again the sum of volumes of the cylinder and the hemisphere. This is a repetition of B. So pi r squared h plus half times 4 over 3 pi r cubed. And we know that they have the same radius, so both radii shall equal r. Hence we plug into the equation the values for r and h, but this time they are not numerical as in B, they are in terms of the variable r. So pi r squared times h becomes pi r squared times 110 minus 3r, which is this expression right there, plus 4 over 6 pi r cubed, which is just half multiplied by 4 over 3. And instead of writing r cylinder and r hemisphere, I've just written r because we know that they are both equal in value. So this simplifies to this expression right there, and hence this red expression right there, which is similar to what was provided in the question. Next, in question E, I'm told using your graphic display calculator, find the value of R which maximizes the value of V. So from our knowledge of previous questions similar to this one, we should be aware that in order to find the value of R, we normally have to differentiate and set to 0. So V dash equals 0 is the equation that I use to find the value of R that makes V maximum. However, since here I only have 2 marks and I'm not required to derive the value of R, I can simply draw this function on the GDC and just find the maximum value. So let's give this a shot. So I've written down the equation for the volume and I've set the parameters of my window as follows. Of course, x minimum and y minimum are 0 because we are talking about radius and volume. You cannot have a negative radius or a negative volume. And with the maximum values, I've played around with them and I've used big values until I could fit the entire graph onto my screen. And here is what my graph shall look like. I want the value of R that maximizes the volume, so I shall just find the maximum point. Second trace maximum. There is my left bound, there is my right bound, and there is my guess. So the maximum occurs at x equals 31.4 and the maximum value is 113,781. Hence, the value of R that maximizes the volume is 31.4. And the maximum volume is approximately 114,000, and I've obtained these values from the values I found on my GDC. In F, I'm told that the designer claims that the new trash can has a capacity that is at least 40% greater than the capacity of the original trash can. State whether the designer's claim is correct and justify your answer. So the old volume was 79,600 centimeters cubed, and the new maximum volume is 114,000 roughly. So I just need to figure out whether this number is 40% greater than this number or not. So I can calculate the number that is 40% greater than this number, which is basically found by adding 40% of this number to 100% of this number. Hence, the result shall be 111,440. I added the number plus 40% of the number to each other, and I obtained this value right there. Now, my volume is 114,000. 40% greater is 111,000 only. So the claim is correct. The new trash can is even more than 40% greater than the volume of the old trash can. So this concludes our question and our video. Take a minute to write the answers down if you will, and I hope you have found this video useful.